All right, batteries, the fuel tank. I mean, this is where you store, this is where all the electrons gather until they get used, right? Typical high energy system will have a large battery bank. And the reason for it is that customer value of, I don't want to listen to a generator in the evening when I'm drinking my sundowner. I don't want to listen to a generator in the morning when I'm trying to make my coffee. Me personally, I didn't want to listen to a generator for 4 days. Our cruising style was we'd go and drop anchor for 3 to 4 days. We never knew when we'd leave, but that's typically what we did. We'd pull up anchor and we'd move away. Now, unfortunately, the deficiency with a 12-volt system, we talked about this a little bit earlier, is I could be at anchor for 4 days and not run the generator, but I had to run the bloody engine for 8 hours to charge those batteries because I had the 12-volt system. Well, if I had a 48-volt system, I'd only have to run it for an hour. My batteries would be fully charged every time we moved. So there's real life examples where we got to. So the batteries, you're sizing them based on how long people want to be able to run without a charging source providing recharging. And that can be the engine, which we're really focusing on here, increasingly solar panels. Solar panels are really, I got another slide on this, they're really relevant in the marine world. We actually have 480 watts on Viking Star, and we'll talk more about that in a bit. Largely, the battery banks these days are lithium ion, and there's a lot of good reasons for using lithium ion. They have reached the crossover point in terms of costs. They have benefits in terms of density. They have benefits in terms of performance. Their charge efficiency is higher. You want to talk about energy usage? Lead acid batteries are typically in the 80%, 85% charge efficiency. Lithium ion batteries are usually 97% charge efficient. So there's another thing you can pitch to your customer. If you have somebody that's using their boat, if they're always tied to the dock, it kind of doesn't matter, does it? But they are very big investment, and you want to make sure you take care of them. And this is where people have migrated toward the Wakespeed when it comes to alternator charge systems, because we have enough control points that we can know what's going on with the battery can tell us what it wants, and we'll take care of it appropriately. Lead acid batteries, the great thing about lead acid batteries is a very mature technology. Been around for 100 years. They're relatively low cost. People know how they behave. They know what to expect out of them. Although there is folklore out there. One of the biggest reasons this whole Wakespeed exists is because of that nonsense that a lead acid battery is only good for 2 or 3 years. If you're only getting 2 or 3 years out of your lead acid battery, you've got a crappy charge system. We got 7 years out of our batteries before it was destroyed by, not one of these, but was destroyed by a shore power charging system. When we were underway and away from the dock, I'd pick up 5 to 10% capacity back in my lead acid batteries because we charged it properly. So lead acid batteries, they got a lot going for them, but they're 100-year-old technology. And we're at the point now where lithium-style chemistries really have a number of advantages, and they've arrived. It's no longer this mysterious thing on the forefront. So in my opinion, there really is very little reason to go for lead acid in a high-energy system. The only single exception might be if you have an environment where the batteries themselves have to charge at low temperature. One of the limits of lithium ion is you can't charge them below freezing. Now you can put heaters on them. In the real world, I mean, our batteries live in the lazarette. It's usually above freezing. In the real world, the batteries live in the coach, the cabin space, so it's above freezing. But I will tell you, one of the first service calls we started getting was, what's wrong with this Wakespeed regulator? It's not charging my batteries. And it's like, where are you calling from? New England. What's the temperature outside? Well, it's like -20. I have an answer. The Wakespeed has just prevented you from damaging your batteries. We realized it was too cold. We knew that the batteries weren't spec'd to charge at that, so we didn't charge them. Warm up your van and voila, things start charging. Okay. The other typical aspects, disadvantage with lead acid technology, and you all know this, rule of thumb is you only use 50% of the capacity. There are exceptions. The AGMs are bare. That Lifeline battery technology that I talked about, I'm sorry, not Lifeline, the Firefly battery technology I talked about, that was one of its values. And it actually worked well. It's unfortunate the company who delivered it, the actual battery didn't quite deliver what was capable from the technology. But typically lead acid batteries, you all know, 50% state of charge, that's the rule of thumb. That there alone gets you over the hurdle of why lithium-ion batteries today are more cost-effective, just because you only need half the amp hours to deliver the same amount of value. Now, because they're smaller and lighter, typically people will go upside if they can't afford to do it. The other thing, I want to point out this very last thing. That right there is the reason the Wakespeed 500 exists. And I'll come back to that in a minute. All right, when we talk about lithium batteries, lithium is just one part of the battery solution. There are other lithium-based chemistries. The ones that we talk about are LiFePO, lithium iron phosphate. LFP is what people tend to refer to it. LFP has a really good charging ability. It has a really good safety ability in the sense that it's one of the, going to the elephant in the room, the thing you hear about with lithium batteries, they catch fire, right? The thing that catches fire is largely the electrolyte inside the battery. Lithium iron phosphate, that chemistry, that combustion point, I think is like 430 degrees C, something like that. So it's a very high temperature. So typically lithium iron phosphates won't be the primary source of combustion. However, if something else starts fire and they raise that battery to over 1,000 degrees Fahrenheit, it will definitely contribute to it. The downside with lithium iron phosphate is their energy density is lower. It's about 30% bigger in order to get a certain amount of storage capacity. You will never find lithium iron phosphate in your cell phone. You will find other chemistries. You largely won't find lithium iron phosphate in electric vehicles because capacity is more important than some of these other characteristics. The downside to those is most of these chemistries have a combustion around 150, 200 degrees C. That's why your cell phone catches fire. That's why your hoverboard catches fire. I am belaboring this point because not only do customers not understand this difference, I will guarantee you when I stand on a number of industry standard committees, the industry by and large doesn't understand it, or there's self-driving motivators to try to make that confusion. When you hear about lithium batteries and you hear about the different, the downsides of the lithium batteries, specifically the F word, little side note, in the RV industry, we never use the word fire. It is a four-letter word. We refer to that a thermal event has occurred. Now, I'm aware of some thermal events that ended up with a couple of frame rails and 2 round axles at each end, but nonetheless, it's a thermal event. It's never used the word fire. I am belaboring this because there is a ton of confusion in the consumer's mind about the dangers associated with lithium batteries. And yes, you have to be very careful with the ones used in here. With chemistries, the NMCs, the ones that have cobalt, the ones that have the benefit of higher energy density. But the trade-off is they're not quite as safe. And if you are using a battery pack with one of those things, you have to take extra precautions. For example, never mount them in the living compartment. There are RV, and that's not a bad chemistry. I don't want you to walk away with that. It's not a bad chemistry, it's just a trade-off. And if that's something you value, that higher energy density, you have to take the steps necessary to have a safe system. Those type of batteries are mounted outside the vehicle in the metal box. Lithium iron phosphate does not have that disadvantage. You can put them in the coach and they can be in a plastic box. That's kind of the sum of the differences. So is there any confusion or questions on this topic? Because it is one that we as an industry are truly trying to educate the population about the differences. Because all they hear is lithium and they think about that scooter that caught fire. Yes, sir.
So lithium iron phosphate, you're saying it's 30% lower energy density than lithium ion?
Then, well, yeah, then like the batteries that go into here, I think 30%. I'm going off the top of my head. Yeah, it's lower energy density. So
How's that compared to like AGM? So it's only like 20. I guess that would be 40%.
well, AGMs are significantly lower energy density, right? And plus the usable energy density is even less, right? And the weight of the fundamental materials, lead versus lithium, is certainly different.
So
Yeah.
when you refer to energy density, presumably you're talking amp hours per pound and physical dimension?
Physical size in this case. Physical size. This phone would be twice as big if it was. Well, I need to talk to him. This phone would be twice as big if it was a lithium iron phosphate battery. So that's why they're not used. Or it would only run 2 hours if it was this big. It's a trade-off. Remember, I came out of the computer industry, and we manufactured laptops first with NiCad batteries and then with lithium, and we went through the chemistries. And it's kind of fun to me to watch other industry discover things about this. Like, we knew what caused batteries to catch fire. And that's why the BMSs were created primarily for the laptop computer industry. That's where that all came from. We knew that those chemistries were more dangerous. And we worked with regulatory agencies. There's specific regulations how you can mail those batteries. That all came about because of being careful with these type of systems and designs, right? So, in a nutshell, 2 walkaways. There are many different lithium battery chemistries. The biggest trade-off, the one we care about is the lithium iron phosphate. They are very safe. The ones used in every other consumer product and almost all EVs are chemistry that requires additional precautions around. And they have additional safety concerns. It's not necessarily bad. I mean, this thing hasn't burned in my pocket yet, but I'll guarantee you there's a lot more thinking that went into this and considerations than yes, ma'am.
Did you say that battery management systems in general came out of laptops?
I would make that statement. I haven't validated, but I would say that's probably true because we were using, it's probably not an accurate statement. They probably came before that. But in terms of battery pack and portable energy, we had cordless drills and stuff, but really the highest energy usage was laptop computers coming out of the 90s. And a lot of development and learnings in that area. Like, for example, I'll tell you a little sidelight story here. Have you ever heard the phrase that when you put batteries in storage, you should keep them around 40% state of charge? It's better on the battery, don't leave them fully charged. If you haven't heard that, go to the battery manufacturers, lithium battery manufacturers, and they'll tell you that. If you're not going to use your battery, keep it around 40%. If you leave it at 100%, it will degrade the battery quicker than if you store them at 40%. Now, I smiled at that because we in the computer industry learned that lesson in the 90s when we transitioned to lithium ion batteries. Because before with NiCads, you wanted your batteries always stored at 100% or the batteries would degrade. So that's what we did. And then we started getting warranty claims because these computers would come off the manufacturing line at 100% state of charge and they'd be stuck in the bloody supply chain for 6 or 8 months and finally get to the consumer and the battery had degraded. Well, people are smart but slow, engineers. We kind of figured out that the problem was that we were shipping these batteries out at 100% state of charge and they sat on the shelf in storage for 6 or 8 months and that was harmful to the battery. So what was our solution? Ship the battery at 40% state of charge. And that is why today, whenever you get a battery, don't care what it is, the first thing they tell you is fully charge your device before using. All right, belaboring this a whole lot. Again, the thing I want you to walk away, because you might run across this with your customer. Different lithium battery chemistries. There's nothing wrong with any of them. They have pluses and minuses, but depending on the one you pick, you have to have additional concerns. For our use, for our use, lithium iron phosphate is the most common and probably most beneficial battery chemistry to use. Okay. BMS, touched upon BS. So lead acid batteries are forgiving. You can overcharge a lead acid battery, well, within reason. You know, you can continue pouring energy into it even when it's fully charged. And by and large, the lead acid battery is not going to care. He's going to off gas, you know, he's going to boil off some water. That's largely what's going to happen. Lithium-based chemistries, these newer ones, if you do that, it will physically damage the cell inside. And I'm not a smart enough guy to know what it does. I know back in Reno, for the company we work for, they've got a building full of PhDs who are smart enough. And if I asked them that question, I'd be deer in the headlight after 30 minutes while they told me what happened. But bottom line is, with these newer chemistries, there are newer restrictions. You can't charge them below 0 degrees C, or they'll physically damaged. You can't continue to charge them once they're full, or they'll be physically damaged. There's a lot of stuff. There are ways that the things will catch on fire if you keep doing stuff that you shouldn't be doing, right? So as a result, BMSs are present in any battery you want, lithium-based battery you want to be using. I was almost going to use the word always present, but never use absolutes, right? The BMS's job is to monitor that battery. The one job that BMS has is to monitor the battery for any overstressing condition. And if it finds an overstressing condition, it will disconnect the battery. That's its tool it can use in job number one. And it's called, it does a disconnect, and it's either internal. In this particular case, they're FET-based disconnects, which I think live, I'm not sure where they live somewhere in that cover. You might have other, like the Victron Lynx, you know, the Lynx BMS, it's got a physical contactor in it. There'll be a disconnect somewhere that if the BMS detects a hazardous condition, that you're either going to stress the battery to damage it, or you're going to create a actual hazard, it'll pull the ripcord and it'll disconnect the battery. Yes, sir?
Is there any considerations for internal, like inside the battery BMS, for the ones that come with that?
Well, that's exactly what we're talking about. Yeah, the BMS, and I guess to your point, there are different ways to deploy this. You can have external BMSs, like the Lynx BMS. But actually, the Lynx BMS, you notice there's a cable that runs to the battery. There's actually, inside the battery itself, another little subsystem BMS. There's actually multiple components that gets distributed. The things that the BMS, whether it's all inside the battery or if it's distributed, that it's monitoring each individual cell's voltage, current, and temperature. And it's looking for a cell to go sideways. It's looking for an individual cell to say he's fully charged and we need to stop. It does on discharge size as well. It's looking for an individual cell to say I'm over discharged and we need to stop for either to protect the battery or protect a safety issue. That's every BMS in the world does that. And that's a massive differentiator between lead acid batteries and these lithium batteries. It introduces complexity. It introduces things you have to worry about. We will talk about load dumps in a bit and down the road. That disconnect can be a catastrophic event on a vessel if it occurs in an uncontrolled way. So a second thing a BMS can do is some of them have the ability to communicate out. They can say, stop doing that. Or they can say, well, keep doing it, but only do it this much. Different levels of communication in and out, and we'll cover the variances when we talk about legacy connections with the Wakespeed, or what I call a wiggle wire, where you have a charge enable, or if you have a CAN bus communication with the BMS. Each of those provide better ability for the charging subsystems and the battery to communicate and provide the safe values that we're looking for. Have you guys ever heard anything about BMSs before other than the phrase BMS? Not a little, okay. Have I explained well what it does? I mean, just in a summary, it's a little computer. And it's monitoring temperature and voltage of each cell, and it's monitoring the current, and the thing it can do is open the charge bus and discharge bus.
So, my question was more, these internal BMSs, if you have a whole bank, several batteries, and
Yeah.
each one has its own internal BMS, how would they work then with an external BMS if they needed one, or would those internal ones for each cell be monitoring them as a whole bank, or each battery, or?
Right. Every battery manufacturer is going to take a different approach. And I don't know if you all heard the question. The question was, how do these BMSs, because you got some that are all internal, you've got some that are internal, you've got some that are all external, you've got some that are a little hybrid, can you mix and match all this stuff? The bottom line is, as a designer, I will sit down and look at where the requirements are for our product and the values we want to deliver and decide how to split these functions. So in the case of, let's take an example of a lithium-ion battery. There are two variances you can get with lithium-ion. You get an external BMS, and that external BMS has got a communication port that goes to every battery. And every battery inside has got a little computer that's monitoring the cells and communicates out the status through that communication back to the master BMS. And that master BMS chooses what to do. The Victron Lynx is the same architecture. There's the external BMS, but it's really more of a collector of information, because inside each individual battery is a little BMS that's monitoring. It's less of a BMS, more of a sensor. It's saying what's going on and typically sending the information up, and then the master BMS decides what to do. Now, again, with lithionics, they offer their integrated BMSs now. And the only thing on the top of it is a CAN port that we use. So it inside, I don't know the exact structure, but I think inside they've got one BMS with wires that go out and sense the voltages and stuff. They don't have it distributed. It's all on one circuit board. That type of architecture is how each battery manufacturer chooses to approach the problem. You cannot mix different brands. You have to get all, because it's a design. You can't take a Ford and put a Chevy engine in it. I know you can, but right. You see what I'm saying? All right. Is there any other questions on the BMS? Because I was told to talk about this a bit, and I want to make sure that we've covered it enough that you guys...
For, say, the Lynx Victron
Yeah.
application that you were talking about, so it's not only going to be compatible with Victron batteries?
Correct. Correct. Because it's a system, right? And it's the Victron system. Yes, sir.
I've got a system I'm working on currently. Consists of 12 volt house bank of 3 Dakota lithium 135 amp hour in parallel. 405 amp hour. And I've got the Victron servo and I've got the GX70.
Yeah.
We're not going to talk about alternators again. That's for another time. But my understanding is the way I'm going to be able to communicate with the internal BMS of the Dakota Lithium is through the software and a laptop.
So we will cover this in more detail. The computer science term is called in-band communication, and it's used the voltage on the batteries. But we'll cover this in more detail. Okay? All right. I'll go ahead and move off of this then. The key takeaway is lithium chemistry is more, I don't want to say fragile, but it's less forgiving. And you have to make sure that it doesn't get abused, and they all come with a little computer inside that monitors the individual cells to make sure that we're not overstressing the individual cells. And that is going to be important when we come back to your question.